In this section we're going to be discussing graphing equations, and where we want to begin is with the concept of a solution point. A solution point, just like it sounds, is a point that solves the equation. Since the equation we're starting with has an x and a y involved in it, then the solution point would be which x and which y would make the equation true. On our graph, the solution points would be every point that is on the actual graph itself. Now, the most basic way to graph an equation is by plotting points. It is not always the simplest way, but it is the most basic way. So you start with plugging something in for x and getting something back for y. Well, the easiest number to start with for x would be a 0. And if you plugged a 0, you'd get 3 times 0 minus 1, which is negative 1. I'll write that over here, actually. So your point is 0, negative 1, which is right there, and that is a solution point on the graph. Then you would plug in another value for x, let's say 1, and you would get 3 times 1 minus 1, which is 2, and there's another solution point at 1, 2. And you see that that's also on the graph. And these are all solution points to that equation. By plotting more points, you could come up with more and more solution points on the graph itself, and then by connecting those dots, you get the line. Now, as you're getting into pre-calculus further and further, your goal is going to be to be able to identify what types of equations produce certain types of graphs. In other words, you can look at an equation and say, oh, that's the graph of this. And in this case, we're graphing a line. So we could start off early and say, notice what's the same is that the power on the variable is 1. And since 1 is a straight line, both of the powers are straight lines, notice we ended up with a straight line. So if you're in an equation with x and y, and the exponents, the only exponents on the x's and y's are 1, then your equation is a line. And that's one neat way to remember it. You'll also learn that when you're in a form of, we're looking at here, y equals mx plus b, and we'll talk about that further later on, that's another way to identify a line. But you're going to learn ways to identify graphs just by their equations. Let's move on to a different type of equation, and let's say we have y is equal to 2x squared minus 3. Well, we would start by plotting some points, and we're going to plug values in for x and get something back for y. Once again, the easiest thing to plug in for x is usually 0, and then plugging in 0, you get 2 times 0 minus 3, which is negative 3, and that is a solution point. So we're going to graph 0, negative 3 as one of our points. Then we'd then plug in 1, and 2 times 1 is 2, minus 3 is negative 1. So at the point 1, negative 1, we're here. And then negative 1 for x, you notice we're squaring, so negative 1 is going to give us the same answer. If we have negative 1 squared, it's 1. 2 times 1 is 2, minus 3 is also negative 1. So the point negative 1, negative 1 is also on the graph. And then we can keep going with 2. We have 2 times 2 squared minus 3. 2 squared is 4. 2 times 4 is 8. 8 minus 3 is 5. So we have the point 2, 5, which would put us here. And then, of course, just knowing that we're squaring a number and anything squared is positive, negative 2 will give us the exact same answer. Negative 2 would also be at 5. And as you plot more and more points, you would come up with the graph of 2x squared, which looks very similar to this here, and it's called a quadratic. So now we've graphed this, and this is the shape of that. It's called a parabola or a quadratic equation, and we'll learn more about that later. One thing to make note of, however, is that point plotting, though it's the most basic way to graph an equation, it doesn't always guarantee that you're correct. in your graph is that because it leaves you to just graph whatever points you've put or solution points you've chosen, and it doesn't guarantee you what happens after you're finished plugging in graphs. Let's, for example, say you didn't use 0 and you only used 1 and -1 and you didn't use 0. You would see these points here. Well, let's see, there's a lot of ways that we could visualize this. You could say it comes down something like this and then goes down something like this, and you'd have that graph, and that's not right. But you could see how that might play in. We could also imagine that the points here, you could say that they could have come down in some way. Just because we haven't plotted points doesn't mean we can't visualize them going something like this. And what happens after those points, we don't know. And the point being is that when you're just plotting points on a graph and you don't know about the general shape of the graph, it leaves you to a lot of imagination as to what the graph could look like. And so plotting points, unless you also know what the graph looks like, is not as reliable as we would like. One thing that you can use when you're graphing that is to your advantage, and they're easy points to find, are called the intercepts. And there are two types of intercepts on a Cartesian graph. And obviously we have the x-axis and the y-axis. So there will be, if the graph touches either one of them, those will be either the y-intercept, meaning where the graph touches the y-axis, and the x-intercept, where the graph touches the x-axis. And that's all the word intercept means, where it touches and with respect to which axis you're talking about. So how would we find those points really easily is to say, well, any point on the y-axis, the value of x is 0. So if we want to find the y-intercept or y-intercepts, there could be more than one, if we wanted to find them, we would set x equal to 0 and find out what that point is. So in our graph, we would have 1/2 times 0 minus 1. Well, 1/2 times 0 is 0, and 0 minus 1 is -1. So this would be the point 0, -1, and you would make sure that that corresponds on your graph. That is the solution point, and it is where it touches the y-axis. So that is your y-intercept. And then we're looking for the x-intercept. Well, notice that on the x-axis, the value of y is always 0. So you can have a x value and a y of 0, which means we're plugging a 0 in where the y is, and you would have 1/2 x minus 1. And now you just solve the equation for x. So we could add 1 to both sides, giving us 1 equals 1/2 x, and then multiply by 2 to both sides. And you get a cancel, of course, x is equal to 2. So we have a point of 2, 0, which is right there, which is a solution point on the graph, and since it touches the x-axis there, we know that's our x-intercept. Now there are situations where in the discussion of intercepts, it is entirely possible to have no intercepts, multiple intercepts. So let's go over some examples of that. In the future, you're going to be graphing circles, and let's say, for example, we're graphing this circle right here. You notice it's not touching the x or the y, so this would have no intercepts. And that's one situation where that could possibly happen. Another situation is where you can have 4 by using a circle, just moving the circle around. So obviously if we had a circle where it was something like this, and of course this is freehand, so you'll just have to assume that's a perfect circle, you have 4 intercepts, 2 y-intercepts and 2 x-intercepts. So there's a situation where you have 2 of each. Now, depending on the type of graph you're creating, you could have just infinite intercepts, and you'll see graphs of that in the future, something like what's called a sine or cosine wave or something to that effect. You could have just multiple intercepts happening over and over again, and that is entirely possible. We also have graphs where you have polynomials, and so a parabola that we have drawn before has, this parabola has in case 2 x-intercepts and 1 y-intercept. And now, just to change color here a little bit, if we were graphing that same parabola the other way, then it would have 2 y-intercepts and 1 x-intercept. So you can see how that can play in. And again, that's just where x and y are equal to 0, and you find them the exact same way. You find them by setting x and y respectively equal to 0 to find those solution points. The process never changes. It's just what type of graph you're dealing with. Now that we've discussed how plotting points is the most basic way to graph an equation, you realize that when you have to choose a bunch of points to get a picture of a graph, that can be quite time-consuming. So hopefully there's a way to shorten that process. And one thing that we can do to shorten that process is take advantage of any time a graph has what's called symmetry. So take a look at the graph of y equals x squared minus 3, and you'll notice that if you vision this line, which is the y-axis, running right down the middle, the graph is the same on the right as it is on the left. So it is what is called symmetric. And the point that it's the same on the left and right of is the line of symmetry, which in this case is the y-axis. So this graph would be symmetric to the y-axis. Now, how do we prove that algebraically? Is to take a look at the actual points on the graph and notice the similarities. So, as we look to the right side, this would be the point 1, negative 2. The next point that's real easy to see right here would be the point where x is 2 and y is 1. And then when x is 3, we get 6. Well, now let's take a look at the left side and notice that when x is negative 1, we also get the answer of negative 2. When x is negative 2, we also get the answer of 1. And when x is negative 3, we get the answer of 6. So what's changed? And what you want to do is to come up with a general way to find this out, is to say, when I pick an x value, it gave me a certain y value by plugging into the function, what we call f of whatever that x is. And that creates a point. In other words, we can write y as f of x, and then of course we have x squared minus 3, meaning we have a function in terms of x. If I plug something in for x, some x value, I'd be finding f of x. Well, now look at the exact same thing on the left side, and notice that what we put in over here was negative of whatever the x value was. So in this case, negative 1. And we got back the exact same answer, which was the same thing, f of x. What that tells you is that if a graph is symmetric to the y-axis, that f of a negative x value, when you plug in a negative x, you get the same answer as if you plugged in a positive x. And that's the way to determine y-axis symmetry. So if you plug in a negative x and you get the same answer, the same equation, then you would have y-axis symmetry. Well, let's try it. Here we have our f of x, so we already know what that is. We have x squared minus 3. If we plugged in a negative x right there, we would have the negative x squared minus 3, which is equal to, well, when you square a negative, you get a positive, so that would be positive x squared minus 3, which equals, so this is my f of negative x, and it equals f of x. And therefore this graph is symmetric to the y-axis. In much the same way as you can have symmetry to the y-axis, you can of course be symmetric to the x-axis. And taking a look at the graph of x equals y squared minus 3, we have the fact that the graph looks the same above as it does below the x-axis. So let's kind of figure out how we can determine that, and you'll see the similarities. And notice that the points here would be where x is negative 2 and y is 1, and then when x is 1, y is 2, and when x is 6, y is 3. And now take a look at what happens on the bottom. At those same points, we have an x of negative 2 and a y of negative 1, and an x of 1 and a y of negative 2, and an x of 6 and a y of negative 3. And notice that the difference is that the y values became negative, but the x's were the same. And in much the same way as when we said that when you're testing for symmetry to the y-axis, that when you replace the x with negative x, you got the same equation. In this case, we're going to replace y with negative y. So replace y with negative y. And if you get the same equation, you have symmetry to the x-axis. And so we have x is equal to negative y squared minus 3. Negative and y squared would be y squared minus 3. And because this is both the same thing as x, then you have symmetry to the x-axis. And that's all there is to finding symmetry around the x-axis. Now before we move on to symmetry about the origin, let's do an example where we can just see how this would save us time in point plotting. Here we're going to be graphing y equals 2x squared minus 1. And what we want to see first is it symmetric to anything? So the first thing we want to do is see if f of negative x would be the same as f of x. And if so, then we are symmetric to the y-axis. So we say y is equal to 2 times negative x squared. We're plugging in negative x, finding f of negative x. And then we have minus 1. Well, a negative of x squared would be x squared. So you'd get 2x squared minus 1. And since f of negative x is the same thing as the f of x, we are symmetric to the y-axis. Which means we only need to plot points on one side in order to finish it. So first, let's make our table, and we have an x and a y, and we want to start with x is 0. And when you plug in a 0, you get y is negative 1. So 0, negative 1. Now all we need to do is plot positive points because we know the negatives of these will give us the same answer. So when we plug in a 1, we get 2 times 1 is 2, minus 1 is 1. So if the point 1, 1 is on the graph, then we know negative 1, 1 is also on the graph. And that's how you take advantage of symmetry. And so we go to the point 2. You have 2 times 2 squared. Well, 2 squared is 4. 2 times 4 is 8. Minus 1 is 7. So we would have the point 2, 7, which means that negative 2, 7 is also on the graph. So you would go to 2 and 7, and 2 and negative 2, 7 would also be on the graph. And now use symmetry to save you half the time of discovering points on your graph. Now let's look at symmetry about the origin. If we're going to be symmetric about the origin, there are specific properties, just like when we had symmetry to the x and y axis. So let's take a look at a graph that is symmetric about the origin and find out what it is about it that we can use as a general way to determine that. Well, we got the graph of half x cubed, and I've graphed it here. And you can do the same thing by plotting some points, which is what I've done. And I've scaled the graph to where every 2 lines is 1, and so on. So these are all negative 1, negative 2, and so on. Okay, now that we have that, we can say let's identify some points. We have the point 1, 1/2, and we have the point 2, 4. Now look on the other side, we have negative 1, negative 1/2. And the point down here of negative 2, negative 4. And now look at what you see there, and is that the positive numbers for the x and y are the same point except that both of them are negative on the left side. So if we kind of think about that, if this is x and y, or f of x, then negative x, negative y is also on the graph. And that's what makes it symmetric about the origin. So what you do to find symmetry about the origin is you say that replacing x, so we want to replace x, y with negative x, negative y, and we should get the same equation. Okay? So now let's do that. We have negative y equals 1/2 negative x cubed. When you cube a negative, it stays negative. So we'd have negative 1/2 x cubed on the right side equals negative y. And then dividing both sides by a negative, that would give you y is 1/2 x cubed. So we found that when we replaced x and y with their negatives, we got the exact same equation, which means that we have origin symmetry. Now, when we're talking about visualizing that on the graph, imagine that to be symmetric about the origin means either we're going to rotate the graph 180 degrees and you would see that it gives you the exact same graph. So if we took this point and rotated it down, you would see that both sides would rotate and it would look the exact same way. Another way of imagining symmetry is to fold it over both axes. So I want you to imagine that this graph is a piece of paper and we've divided it in half vertically and horizontally. You take the bottom and fold it up and then fold it over and imagine what it would look like, and it would look the exact same way. And that's just neat ways to kind of visualize what would happen to the graph. What I usually personally do is to just rotate the graph around and see that it looks exactly the same, because that's what it would look like with origin symmetry.